Just give me a second. Seems like I'm not able to hear properly.
Yes,
Right.
yes, it's audible. Fine,
All
clear.
right. Perfect. All right. Am I audible to everyone?
Yes, sir.
Yes, yes.
Oh, perfect. Yeah. Hi, Darshan
Uh,
sir.
uh,
How are you?
yes, yes. Good morning, good morning. Fine,
Yeah.
fine. Welcome to you.
Sure.
Professor Amit, please start your session.
Okay, sir. Okay. So, respected participants, very good morning to all of you. On behalf of EC Department, I, Professor Amit Choksi, welcome you all in this 1 week FDP on Internet of Things, which is sponsored by the AICTE ATAL. So, today we have three sessions, and in the first session, the topic is on security issues in IoT, which will be delivered by our domain expert, Dr. Trusit Sasar, who is also our EC Department BVM alumni member. Now, before starting session, I will brief out the introduction about the Dr. Trusit sir. And the Dr. Trusit sir, who loves to build a solution for software and hardware industries. He has designed and developed the software architectures for a variety of software and hardware technologies, including the Internet of Things, augmented reality, and indoor positioning and navigation. He has a background in both software and hardware engineering and has a expertise in the embedded system and wireless sensor network. Currently, he is a software developer at Amazon in the AWS IoT team. Prior to that, he did PhD in computer science from the University of Texas at Dallas with a research interest in the security and privacy issues in IoT and under customizable IoT architecture. He completed his master's degree in embedded system from BITS, Goa, in India. His research during his master's degree was cross-layer wireless sensor network protocol. He was part of a research group at Wireless Sensor Lab in BITS, in BITS, Goa, in India, where he led a team of 500 graduate students in designing a wireless network for Gas Authority of India Limited Company. His contribution helped the project to raise a fund of 90 lakhs rupees. So his final year project during his undergraduate at BVM Engineering College was a prototype similar to Google Home. He also provided a solution to local embedded system based industries as a consultant while pursuing his undergraduate and master degrees. So on behalf of EC department, I welcome Dr. Prasid sir. Now,
Thank you.
without taking too much time, I will hand over this session to Dr. Prasid sir. Please, sir.
Yeah. Thank you so much, sir. Such a warm welcome and nice introduction. Uh, so let me start my presentation. All right. Right. Can everybody see my screen? And is the PowerPoint on the screen?
Yes, sir.
Yes, yes,
Yes.
it's seen.
Perfect. So, as you all know, today's topic is security issues in Internet of Things. And I'm Trusit. I currently work as a software developer in the IoT core team of Amazon Web Services. Uh, Prior to that, I did my PhD, and the topic for my PhD was reliability and security issues in Internet of Things. So, security issues in Internet of Things are pretty wide topic. So, I'll try to cover as much as I can in today's presentation, and hopefully, by end of this presentation, you will know a little bit on like what are the security challenges and what are the issues we face during Internet of Things present. So today's outline, first we'll go through a basic introduction of IoT, and after that we'll discuss IoT security from the uh, pretty basic abstract view, and then we'll discuss a little bit some on access control in the IoT, which is a pretty dominant issue in terms of user privacy for IoT devices. And at the end, we discuss about denial of service attacks, which can be led by Internet of Things devices. So let's start with like basic concepts of IoT. I know this talks on IoT has been going for like almost 3 to 4 days. So can anybody tell me what is IoT? I like to have this thing more like interactive. So uh, anybody or like what is IoT, Internet of Things? All right. So internet is basically made for humans to use, and we do use it for various purposes like uh, doing watching videos on YouTube, uh, talking with your friends on WhatsApp, or we are using Twitter for tweeting stuff. So there are a lot of use cases for internet, and most of them are built around users, which are humans. Now, in Internet of Things, we kind of extend this idea to the things. So this means it's not only users, but even the things can use the internet. So in short, for IoT, it can be summarized as 3A concept: anytime, anywhere, anything can connect to internet. So basic idea behind Internet of Things is like anything which you have, which is anywhere inside, anywhere in the world, should able to connect to internet anytime. And that's the broad abstract point of idea for Internet of Things. Now, IoT, the concept was given in 1998. And during that time, it started as, you will put the RFID tags on devices, try to see how those devices move specifically in the area of supply chain management. But in few years, it started becoming a global sensation, and people started using it a lot other places. Specifically, now it has been used widely in smart home and other places.
Sorry
If
to
you see
interrupt
this,
you, Mr. Trosit. Sorry
yes,
to interrupt you, Mr. Trosit. Can you go back to earlier slide, please?
sure. Does you have any question on this slide? Hello.
No, no. It was so fast that we couldn't correlate ourselves, actually. That's why I
Oh,
wanted to see that.
so it just went away. Okay, feel free to interrupt me in case if you face any technical issue or if I'm going so fast. Uh, yeah, I can't see anything other than my PowerPoint on my screen. So yeah, if you have anything, just feel free to interrupt me. Uh, so yeah, I was mentioning about the second graph. So in the second graph, you can see that initially it started with low number of internet connected devices. Now we already have like 50 billion devices, which is almost 6 times than the number of people in the world, and it is growing exponentially. You see the exponential graph here. By 2025, it's expected that we're going to have like 2 trillion devices, and that big number makes a big difference when we talk about security. Like just imagine only a single 1% of devices having trouble or having some security vulnerability, that still would contribute in like billions of devices being compromised. And for that reason, securing IoT devices a pretty important issue. Now, let's talk about the threat model. Now, it's kind of hard to put together a threat model for like generalizing whole IoT because there are thousands, not even thousands, like millions of types of different devices available in the market, which does various of different things. So we cannot like generalize the actual threat model. But if you want to like broadly categorize it, it can be categorized in like 3 main categories. First is take control. Like if someone has access or someone find a vulnerability in an IoT device, that person can take control of that device, steal information, Just imagine like you have an IoT device, Alexa or maybe Google Home, and someone find a way to buy like get access to it. Basically, that person knows almost everything you are doing at home, so they can use it to steal information. And the last part is disrupt services. Now, these disrupt services can be divided into two parts. One part is disrupt the actual services of IoT. So let's say if someone gets hold of a million IoT device, that person can actually stop all those million IoT devices working, or that person can actually use that million devices to send requests to some website, let's say Google or Facebook, or maybe some other website like GitHub. They can actually take down that website. So at the end of the presentation, we are going to discuss those scenarios for like distributed denial of service attack, which can be possible due to uh, vulnerabilities in IoT. So this is like pretty much broad category of threat model we see when we talk about IoT. Now the next thing we'll talk about IoT security. Now there are various components of IoT security, and the main components are CIA, uh, confidentiality, integrity, authenticity. After that, it comes to access control. Now, access control means it will provide details like which IoT devices access to which IoT services, or which app on your phone can access to one of your IoT device or not. So that's comes under access control. And then the last part is user privacy. So user privacy is kind of extended version of access control, where using access control, we make sure that the data which user has is private enough, and no app or no other IoT device is misusing that data, or collecting data without user knowing about it. So that comes under the user privacy, which is kind of extended part of access control. Now let's talk about confidentiality. Now, in confidentiality, we want to make sure that when IoT device communicates with IoT server or other IoT device or the app which user has, the communication between that device to the other party is secure, is confidential, that no one else has access to. So let's say there is an IoT device sending a message. Now that message is not encrypted or weakly encrypted. IoT servers receives it, but here is an issue. An attacker can snoop message and know what the message was. So this is kind of an issue in terms of confidentiality, that now the information shared between the IoT device and the IoT server is not confidential. And there is a person who can actually know what messages are being transferred. The next part is integrity. Now this goes a level ahead of confidentiality. Same way IoT device tries to send something, the message is not encrypted or it's weakly encrypted. Now this time attacker snoops the message, and now attacker not only wants to know what's being transferred, he actually wants to alter it. So uh, if IoT device sends a signal to another IoT device to turn on, now attackers captures the data, alters the message from on to off, and sends the altered message to the IoT server. Now it's a slight difference here. The difference here is you don't see a line here to here. Like from IoT device, the message is not going to the server directly. It's going through this attacker. So this is a special case called man in the middle, where this attacker poses itself as an IoT device to IoT server, and it acts as IoT server to IoT device. So it's kind of a man which is sitting in the middle and just keep altering the messages. So this is a kind of a serious threat, the integrity, that we want to make sure that when message A is sent from IoT device to IoT server or another IoT device, it's not altered. The next part is authenticity. Now for authenticity, we have IoT device sending a message using a weak authentication mechanism. So the authentication mechanism used between IoT device and IoT server is weak. Again, the attacker snoops the message. And now after snooping the message, attacker knows that how IoT device is being authenticated with the IoT server. He knows what are the keys being used. And now he can pose himself as an IoT device. And now in future, all the messages this attacker can send posing himself as an IoT device. So this is kind of the part of authenticity and which kind of part of CIA. Now authenticity for IoT, it has like two major parts. The first part is device authenticity or device authentication, which is like actual IoT device and IoT server, they are actually uh, being authenticated to each other. And the way it happens is like each and every device will have a unique key. It's like a more like a username password. The way each user has its own username and password, that device will have unique key to authenticate itself. It must be lightweight. We all know IoT devices are lightweight, so should be lightweight. And there are multiple suitable ways. I just mentioned two of them. One is public key. There is three-way mutual authentication can be used. Uh, the next is message authentication. Now this is like once device started a communication to the IoT server. Now all the messages device is sending to the server, we don't need to authenticate device again and again. Just imagine you log into Google and after logging in, you send one email. Now, when you send another email, they won't ask every time you do perform a task to do a login. So same way, like every time you perform a task, it's kind of a message. So you just need to do one authentication, the one which you did. That's called device authentication. The message authentication happens like after device authentication, all the messages you send would be authenticated using message authentication. So this is like messages sent after you did the authentication. It's generally done using session keys. So once the authentication is done using this unique key or username or password or any other mechanism, they establish a session key, and that session key is used to authenticate. Again, it must be lightweight, and suitable method is shared key HMAC based authentication. I'm not going too deep into this because they are like itself kind of a whole presentation to discuss like public key, three-way mutual authentication, or shared key HMAC. But these are kind of security mechanisms to make sure that authenticity of an IoT device is maintained. Now, how to achieve CIA? Like, do we have a kind of a magic potion which does all those things and we don't need to worry about it all? It's kind of we do, and we actually use it pretty often, like in our day-to-day life. It's HTTPS. Like if we use HTTPS, uh, it covers all three parts of CIA. It provides confidentiality, it makes sure that your message integrity is maintained, and it makes sure that once the device is authenticated, no one else can authenticate themselves as that device. So if you use HTTPS, the CIA is maintained. Now, the very first thing came into anyone's mind when we talk about HTTPS is, doesn't it heavyweight protocol? Because we just talk it should be lightweight. But the way IoT devices are manufactured now, like most of those companies or most of those people who design IoT devices, they create kind of a device gateway which can support HTTPS and which is talking to the IoT server. All the other devices talk to the device gateway through some sort of other low-level security protocols like CoAP or DTLS, or in some cases LoRaWAN. So we can still have kind of a hybrid architecture where devices communicate to the gateway through LoRaWAN, CoAP, or DTLS, and then gateway communication with the actual IoT server using HTTPS. So that's how we achieve CIA. Now, there's not much challenge here on CIA. The reason is it has been done for normal security, and there are a lot of protocols and a lot of other research done for like 25, 30 years ago, and it has been used pretty much everywhere. So not going to talk much about CIA or HTTPS. We all use it and we all know it's pretty secure. The next part is the authorization. Now, before I go further, is everybody able to see my screen properly and hear me properly?
Yes.
Perfect. Yeah, just want to make sure, like I'm not able to see you guys, so yeah, just checking in that everything is fine. Good. And yeah, please feel free to interrupt me anytime you have any question. Authorization. Now this happens after the authentication. Now in authentication, we perform that. We make sure that the IoT device which is sending message, it's actually the IoT device which it's saying it is. Now in authorization, we perform that the device which is sending message, whether it's authorized to perform that action. So if one IoT device sends message to another IoT device, let's say you have a door lock and there is another IoT device, Google Home or something. If Google Home asks your door lock to open or close, does the app which is using Google Home has that authorization access to do that? That part is covered in authorization. So it basically validates whether an entity has an access to given resource or not. It's basically policy-based mechanism. We'll talk about policies later in other slides. Some of the examples. Now we do see this authorization pretty often. It's just that we don't realize it, that it has been done. One of the example which came into my mind the very first is the Facebook friend list. Now I'm sure that all of you has Facebook and you all might be using it very often. Now, when you see someone's friend list, Facebook provides you three options: that everyone else can see your friend list, only your friends can see your friend list, or only you can see your friend list, no one else. So based on the settings you said, let's say I said only friends. So anyone who is not my friend is not authorized to check my Facebook friend list. So this is the resource which a person wants to get access of. But this policy, this three thing which is a policy, makes sure that whether that person has access or not. So this is a pretty basic example, and it's not only Facebook. All the social media sites which we use, they all use authorization in one way or another. The other example is file access in your laptop or desktop. Now in Windows, it's kind of subtle to know, but for Linux, you can always see that it has three kind of file access: read, write, and execute. And we have three types of users like root, user, and group. Now the way we store this thing in authorization is we have kind of a table here. We have read, write, execute, access. So this is kind of a access you want to have, and this is the users, like root user, a given user, or a group of users. And if it is one, means that it has the access. Zero means it doesn't. Just to give you, it's just for an example. This is not the way Linux stores it. It has a different way of storing it. This is just to give an example. I just provided this table, but this is not the exact way Linux stores it. But authorization, they generally have this kind of a table where you just put values 1 and 0 and make sure that you have the access or not. Now, let's talk about access control. Now, access control is kind of done, or it's a another extended version of authorization. So access control is a authorization is a part of access control. So when I say we want to have an access control mechanism, we perform authorization operation to make sure that our we have proper access control in our system. Now, it's basically control which user has access to which resource. So basically authorization, and it has certain terminologies, object, which is like resource being accessed, a subject, which is a user who is accessing the resource, and there is a reference monitor. Pretty basic diagram for this. There is a subject trying to access a resource. Now this is the reference monitor, which I'll show you what exactly it is in the next slide. And this reference monitor will decide whether it has the access to that object or not. So that's the terminology diagram for the access control. And let's talk more about reference monitor, the main heart of this diagram. Now it's kind of rules. So in access control or in authorization, it's pretty much simple rules. A rule will say that, hey, whether a subject A has access to resource R. That's it. So it's basically set of rules. We just need to make sure that we follow those rules. And those rules will provide only two output. We grant it or we deny the access. That's it. So it's basically a bunch of if conditions saying certain things. Now we can store access control. We already showed you the one method, this metric based method, like in the previous example. So this is our object, like a list of objects O1, O2, A3. We have subjects S1, S2, S3, and now here it says that whether subject S1 has permission to write to O1. So this R and W says S1 has both read and write permission to O1. S3 doesn't have any permission to O2, but it does have read permission to O1. So by just reading at this table, I can actually deduce that which subject has access to which object or which resource. Going further, does anybody see any issue here? Like there is a specific issue in terms of amount of space we are using here. Can anybody point out the issue? So if you see here, when S3 doesn't have access to O2, what did I did? I just put an empty, so even though I say dash, in computer, I store some memory. I just say a zero or some value. So that means I'm writing a zero or something, which is kind of making it store certain more values because I'm writing zero here. That means I'm storing more values. Here I need to store 9 different values here to store. And out of those 9, 2 values are useless because it just says that it doesn't have access or it's just zero. To make it proper, we can do something like this, where we provide an object here, and we just list who has the access. We just don't mention the users who doesn't have access. So O1 has access, read access for what? S1, S2, S3, I mentioned here. Write access to S1 and S2, I mentioned here. So this way, we can actually store or we can actually save the memory. Just imagine you have like 1,000 users, 1,000 subjects, 1,000 objects. It will take a lot of memory to store. It's like 1,000 multiplied by 1,000, it's a million or 10 lakh different values we need to store. And it will happen that, out of 10 lakhs, 5 lakhs values are just empty. You don't need to store any values. So this is not the most efficient way of doing it. But yeah, if you create something like access list here, it will definitely save a bunch of space. Now, even the last one, the access one, we saw it's not perfect. it still has some issues. The basic issue it does have is, just imagine you have 10,000 users, and out of those 10,000 users, a set of users, they have similar kind of permissions. Let's take an example of a university. In university, all the students will have similar kind of access, or specifically all the students of EC department will have uh, specific kind of permissions. All the teachers will have specific kind of permissions. Now, if I keep storing all those values with like ones and zeros like this, yeah, it will just waste up a lot of my space, because I'm just gonna write for like 500 students. Okay, read permission for all this thing, write permission for all these things. It will just take up a bunch of my space. Now, to make it easy, we can make it something called role-based access. So now I'll create a role. A role would be, oh, EC student, and I'll assign permission to EC student. So anyone who is EC student will get that permission. So that way we can save a bunch of space. And this is like role-based access model. Now user can have one or more roles. It's not necessary to have a single role. And here is the terminology again. Now its user is basically subject, but because it's kind of a role based, it's more appropriate to call it user. So that's why they call it like user. User has a role, and we have object, and then we have sessions. Now we'll discuss why do have sorry, why do we have sessions? Sorry. So we have user. Now user have multiple roles. Now it might happen that two roles collide with each other. For example, first role says that, oh, grant the permission. Another role says that, oh, denied. That way, now we have a collision. And because of collision, it will make it impossible to provide the permission, because two different roles, they are actually kind of colliding with each other. That's where session comes in. When a user tries to access the system, it will create a session, and in the session, user will provide which role a user wants to use. And based on that role, it will get permission. So this way we make sure that we'll never have a colliding situation where multiple roles can say different opposing results. So that's RBAC. And now we come more near the IoT trend. Now, RBAC we do use in IoT a lot, where we provide rules to different devices, different apps, and different users. But it's not enough. The thing is, the rules can grow pretty big, because we have billions of devices, and there would be a lot of users using it. So keeping track of rules might be hard. Now to have, and plus things changes pretty often. Like we provide permission to certain devices. We just wanted to give it for a small fraction of time, or maybe just for one session or something. So it's kind of hard to create roles that fast, delete roles, or change roles, or edit those things. To avoid that, we use something called capability-based access control. So in that, access is granted to request based on the access capability. We'll see about this thing later, like what exactly the capability-based access is. But it's generally a token or a session key. So a user tries to communicate with, or user or IoT device tries to communicate with the IoT system. It authenticates himself or herself or itself, and then there would be a token or a session key provided to it after the authentication based on the capabilities it has. Capability means what are the permissions it has. And using that token and session key, it basically performs the task for whether it can actually authorize for certain tasks or not. Generally, these tokens are generated via server or a trusted entity, and in many cases, it was actually provided by the user itself. So device A tries to communicate with device B. Device B will ask user, hey, device A tries to communicate. What should I do? Should I grant the access? User say yes, and then the access has been granted, and now device B actually stores the result that, hey, device A said yes to do that. So this is kind of a capability-based access control, better than rule-based because it's dynamic. It can scale without an issue, and there is no centralized way, so centralized place to store all those things. So it's kind of distributed too. So that's capability-based access control, which is widely used in IoT. Like most of the IoT systems now, they use capability-based access control. And again, it's built over role-based access control. So you have role-based access control. On top of that, you create actually this category-based access control. Capability-based access control. Now, talking about access control, let's talk about something called access control over privilege. Now, here is an example of providing more access control than the previous one, more access control than the one which it should have. So in this image, you see this part. So this is kind of a door lock, and a door lock has few functionalities. One is you can read it has a battery, so you can read the status of a battery. The functionality is you can lock and unlock the door. And the third functionality is you can know what's the status of the door. Now, there is a client app which asks user that, hey, I want to access your door because I want to show you how much battery it has. But in backdoor, it actually tries to lock and unlock the door or know the status of your door and send that data to the server. So this is clearly breach of your privacy, and it also disrupts your services. So yeah, this client app is malicious and doing all those bad things. And it's doing because of something called overprivilege. Now, how we can avoid it? A pretty basic, simple example would be functionality-centric access control. So now here we see that whole access control is given for this whole thing. It's not given per function, it's given per thing. So what if we just give per function? That solves the problem. We separate each functionality of IoT device. We kind of provide access control for each functionality. It has three main key approaches. Fine-grain access, which like your access control now is like pretty fine-grained, so you are giving only the thing which is needed. You isolate different functionalities. And the third one is pretty much similar to the first one. It's like least privilege. Like the privilege which is provided is the least possible privilege a subject can have. Now, this is a simple example here. This is a client. It can be an app, or it can be another device. It can be a user. Now, it doesn't have access to thing B. You can see here. It does have access to thing C. For thing A, this is more like our door. It have access to one functionality, which is like reading the battery, but it doesn't have access to first two. So which makes it much more better than the previous overprivileged one, that it doesn't have these two functionalities. Now, how do we store it? It's pretty much similar metric-based method where here, so this is more like this is the thing, and it has this functions and what state it is now. And here, like this app ID, or this is more like a user. It can be another user. It can be another IoT device. It can be an app. But the person who has been researching on this thing, they are more focused on the app. So that's why I say like it's an app. And for the app, they got like only this function, like lock app has the state. It can set the status of the lock. It can read the status of battery and so on and so forth. So this way we can actually make sure that who can actually set the status, who can actually get the status. Here are some rules. Now, these are more like policies, like the one I mentioned in the very beginning of the access control or the authorization. It's the word policy. These are the policies. Like this policy only says like, oh, it only allows to read battery readings. Oh, this one allows to like check the door status, and actually you can lock the door, and you can. So for using stat, you can actually lock and unlock the door. Now, this one gives like all the permissions. For battery, we cannot set status to the battery. If battery is 30% charge, you cannot make it 40% charge. So it's always it always have only read only. That's why it only has a gas status. For other things, you can do both read and write. So that's why it's on. Clearly, it has some issues. The first issue is too many permissions. Like just imagine, I have 10 devices at my home. All of them has 5 functionalities. I need to maintain like 50 different permissions. Too much to work with for a normal user to just manage all those permissions. Privilege can be misused. Now this is crucial. Like just imagine if there is an app which says that, okay, I'll open and close the door when you come near the house. Okay, and you gave permission to it, and yeah, it actually opens the door when you near your house, but it has the permission, and it can actually open it when you are not near house too. So it doesn't have a context attached, so it can do this thing anytime it wants. So even though we say that we are providing the least privilege, based on context, they can actually be misused. And to avoid that comes the next part, is the context-based IoT access control. Now, we had first the role-based, capability-based access control, where we can actually perform access control based on the role, based on the capability. Then we realized, no, we can actually provide overprivilege. So we came up with something called functionality centric. Not enough, because based on the context, user can misuse it, app can misuse it, other IoT device can misuse it. So the next idea is like, what if we just make it context based? And for context based IoT access control, use context. Now, what's context? It's kind of more like the scenario surrounded by. So let's say when you go near the house, the app open the door lock. So the context is your location is near home. That's the context. So for that context, if it is the first time showing up, the IoT system will ask permission like, hey, should I grant it or not? If it is granted, it will store that, okay, the user has granted this context to allow. Next time similar thing happens, next time you go near your house, the door will be opened because it already had that context. If a new context appears, it will again ask for the permission. So that's like basically context. It's more like a scenarios near you. Now, it's kind of a reference of usage. For example, time of request, at what time it happens. Source IP address of the requested user, who is requesting it. If it's IoT device, which IoT device, if it's a user, which user, if it's an app, which app. And other IoT device status, as I mentioned, it checks the location, like, hey, your mobile phone says that, oh, it's near home, and at that time you open the door. So that's kind of a context you have. So now you make sure that any other IoT device or app is not misusing the privilege given to it, because we are actually tying a context to it. This can be broadly categorized in code-based context, external environment context. Now, external environment context is more like this, like other IoT device status. Code-based context has like this, like source IP, who was the user, what was the time request. So that's kind of a code-based context. We'll talk more about code-based context. For external environment context, it's still under research. There are a lot of researchers working on it, but we don't have a concrete solution yet. So yeah, there is nothing which I can present because it's still under research. One of my teammates back in UT Dallas was actually working on that, and probably he's still working on it. I haven't been in touch with him, but he has been working on that thing for a year ago. Now this is a little bit a different, the code-based context specifically, if you don't have a lot of coding background. So I'll try to make it as simple as I can. So different code part taken during the execution considered as a context, and it considers few things into account as a context. UID. So you don't need to confuse UID or GUID. They are basically a unique identification given to each IoT device or a user or an app which is trying to access the IoT device. A control flow of the code, data flow of the code, and runtime values of the code. Now, it may look really confusing, but I'm going to show you some examples of control flow and runtime values, and I hope after that it will become much more clear. So just imagine this is the kind of algorithm or the diagram of our code, like a code is being executed something like this. And so here is a condition here, like if a condition is true, you execute code B, you execute code C, and then you execute code F. If condition is false, you execute D, E, and then F. Now at the stage F, it needs to actually communicate with one of the IoT device. Now first time when we execute the code, this condition become true. So it went through A, B, C, F. And when it went through, this is the first time it happened, it asked user, hey, I am seeing a context here like A, B, C, F. Would you allow to open the door or do something? If user says yes, anytime, when this context is followed, it will always say yes. So this is how it stores the context, and this is how we can actually see the context-based thing. So this may be something like the A would be like when you are near home, if it is true, you go like, you fetch the context or fetch the details of the door lock, you communicate with the door lock, and here you ask the permission for the door lock, and it's open. If it is false, you again do the same thing, and then if you ask, I said, no, I'm not near my house, seems like someone else trying to do it, or the app is behaving maliciously, so don't open it. So anytime now this code path is followed, we understand that it's malicious and it has some wrong intended user behavior. So either the app has been compromised, someone else hacked it or did something, or someone else hacked another IoT device and causing this flow, which I'm not approving. So this is how it works. Now, similarly for runtime, let's say the first time when I have this ABCF approved, the user's location was home. Now next time similar path happens, but user's location was away, not home. So based on the runtime value, the context changed. And now because context changed, the IoT device will ask for the permission like, hey, seems like last time you approved this thing, but you are at home when you did it. Now you are away. You still would like to do that? And based on that, user might approve or disapprove. If user approves, it will store. If user disapproves, it will store that, hey, when user was away, something like this happened, and seems like it's a malicious activity. Now, this is kind of a patching, like, this is, let's say there is a code where it just says that when user is away, switch off this thing, uh, switch off the camera. So this is basically a code snippet for Samsung IoT code where it says that somebody kind of maliciously pushed this code inside the actual working app where it says that you switch off the camera when user is away. This is wrong. You shouldn't do that. Like, you want your home cameras to be on when you are not at home. But somehow somebody pushed this kind of malicious code, or maybe app did it purposefully because they want to uh, do some malicious activity. Now, this can be avoided by like this, where when you ask to switch off, it actually asks users permission here, like, hey, would you approve this thing? And when you got a response, based on the, if it is allowed, you allow it, otherwise you won't. So this is basically kind of patching the code in a way that you make sure that all the things are happening in a secure way. Another abstract point of view, how request model works. Sorry. There can be multiple triggers to open a window. This is a good one. Like, if temperature is greater than 100 Fahrenheit, yeah, you open the window because you are feeling really hot. This is a good intent, but this is a malicious intent where when home mode is sleep, you just do it because somebody pushed the wrong code into the app, or somebody did a malicious activity. And based on that, we can actually approve or deny the context, and based on that context, this thing will be authorized. So this is like a really nice way to make sure that based on context you approve or disapprove some of the policies for IoT. Some of the disadvantage, it looks pretty solid right now. Initially we had nothing. We had only role-based, capability-based, over-privileged thing. After that, we found like, oh, we can actually do better. Do functionality-wise, we found no functionality-wise, we still have an issue. Maybe someone can use it out of context. Now we found context-based things. Now, what better we can do? But the number of contexts would be a big disadvantage here. Just imagine, like, you can have, like, in some cases, hundreds of contexts, and for each context, if app started asking you, you'll be tired to allow and disallow. So permutations and combinations would be extremely high here. Other thing is similar values. Let's say you are working on some agriculture place where context is changing based on your pH value of your soil. Now pH value of 6.9 and 6.8, they're pretty similar, right? So if something happened at 6.8, it should happen at 6.9 too. But the thing would be, in context-based system, you may not able to differentiate them, and you will keep asking user, hey, should I approve it? Now this will make users' life miserable because any value between 6.5 to 7 might be similar, and it's keep bugging user to approve it. So yeah, that will make life of the person who is approving it miserable. What can be a potential solution? We can have a machine learning based approach to categorize context. So now if we have a way to categorize like 6.10 and 6.9 in the same bucket, that hey, they both are similar, we can actually make this thing better. So a machine learning based approach can be used here to do that. And yeah, there are some researchers actually working on this thing. Now, we talked about two things here. So if you remember, we talked about three different ways someone can actually disrupt the IoT thing, or someone can hack, someone can do if it has the access of IoT device. He can actually can take users' private data. We talked about it in CIA. It can, the person can actually do some wrong things on IoT devices. Oh, we already discussed it in access control, and we talked about context-based, functionality-based access control. So now we know that these are the two things covered. The last part, the disruption of service. Yeah, we haven't covered it yet. That's what we are going to cover now, that how a user can disrupt the service if he has a lot of IoT device. Now, the thing is, the previous two parts more like theoretical. Like we didn't see big number of attacks happen using those two, but this DDoS attack, it happened in October 2016. Yeah, October 2016, a big attack happened called Mirai. And this is the example that if you have gain access of a lot of IoT device, you can do a big harm to the internet community. And we'll see in this section that how it can happen. Now, let's talk about the threat model first. So basically, all these IoT devices you get, a lot of those devices come up with uh, a SSH port or telnet port. In many cases, those SSH and telnet ports are open. In some cases, they are not open, but they have default username and password. Now, a lot of you who has their modem at their home, they might have a basic username like admin and password also admin, or username admin password is password. Yeah, if you do have it, make sure you change it, because there has been multiple attacks in past which actually exploited this default username password vulnerability to do a lot of harmful things. So uh, make sure if you have it, just change it. So yeah, they try to log in. Like if it's like this, they try to log in, and once they have the access, they just deploy a malicious script, like to gain the user's data, or just to attack another system, or to shut down your system. So that's what they are doing, like deploying scripts to do all these things. And here is an elaborated example of these three sentences which I just said. So it's like stepwise process. So we have a kind of an existing device which looks for other device that, hey, uh, is there a port, is there a device which is using default username and password? If once it finds it, it kind of actually port the once it finds it, first it sends the details to CNC server. Now CNC server is kind of command and control server, so it kind of commands all those boards. So it sends the detail to CNC server. Now the CNC server sends back the virus or the malware to the newly acquired device. That it may be something like to disrupt other services, or it can be anything. It just sends there. And now, once CNC server finds out, hey, now I have million devices or 10 million devices. Now just let's attack one of the internet service. And this all million or 10 million devices start sending data all to this victim. And this victim site can go down because it doesn't have enough capacity to just handle all those requests. And these requests are just fake requests trying to actually disrupt service for this victim. So this is basic threat model for distributed denial of service attack. So this is distributed because there are like distributed boards, and denial of service because they're kind of trying to disrupt their service by sending fake requests. Now, in early days, late 1990s, early 2000s, there was something called Bashlight. This was the very first malware created on DDoS, which was using similar mechanism which I shown before. It's like server client mechanism, and it just scans once it has enough devices, sends the attack. It scans for open telnet ports, try to log in, and for attack, it's just wait for server's command, and once server sends the command like, hey, just create a DDoS attack to a specific IP or specific service. There are variants. Like this was the very early, one of the earliest DDoS attack script or DDoS attack malware. Another was Qbot. It improved scanning for IoT devices, mostly added open ports for the IoT. Like it find out that IoT devices has such kind of ports which are open, so it just improved there. BLJ, now they are smart. Like they just make like, okay, what if we make the communication between C and C and all of our bots encrypted? So their attacker, they try to think smart and they actually use some of those encryption mechanisms. And now here comes uh, the biggest attack done using IoT devices, Mirai. It happened in late October 2016. It was similar to Bashlight, but it has something called like additional loader unit. It used 48 default username and passwords. So those can be like username, password, admin username. So there are 14 sets of those. They tried it on open IoT devices and to avoid detection. So it might happen that at some point, you can someone is trying to find this kind of malwares. They may be able to find it. So what they did is they didn't store the script on IoT devices. So once the IoT device was restarted, the malware is no more in the IoT device because they kind of didn't store it in it. They just store it temporarily. If you restart it, the script will be gone. Um, so yeah, that's what they did. Another thing they did, which was pretty impressive, that they make their source code open source. So you can still go to GitHub, look for Mirai, and yeah, you will see that the actual source code of malware they use to actually hack all the IoT devices. So yeah, that's pretty impressive. You can still go there. Yeah, I suggest not to use it, but you can still go there and check. So yeah, here is the infrastructure. Again, pretty simple. It starts with so it starts with here, like there is a boat. It starts, so there is this boat. So initially when there is no boat, they actually started from their server to acquire few initial boats. Once they acquire few initial boats, it started scanning. Once they scan, they find some victim, like, oh, looks like there is this thing which has open ports and it's not secure enough using default username password. It report the server like, hey, I found something. And server now send it to the loader. Now this is a new part. Like previously, command and control server does all these things. Here, this report server dispatches to loader. Loader will load it. It's pretty same. It's just they just divide it into two parts so that they can scale loader separately than the report server, because uh, this will require more bandwidth because it's sending more detail. It's just like communication. So they have a loader kind of to make sure that it's scalable enough. Once it's load, now we'll wait. We'll wait until we have a lot of devices, a million or maybe more. And once you have it, there would be an attacker sends a command to command and control, and the command and control will just ask all those devices to attack a DDoS target. They did it in late October 2016. Tried to disrupt few services, and if I remember correctly, there are few services which got disrupted, and there are others which mitigated it pretty fast. Now they send a lot of attacks. They send HTTP flood. They said UDP plain flood, UDP flood. So basically what they do is they kind of send a request to connection, and then they don't accept those. So that this sync flood, acknowledgement flood. So basically what it does is they send the request for like, I want to create an HTTP connection, or I want to create a TCP connection. The server which is receiving this will kind of allocate some resources. Once they allocate the resource, this one won't respond back for acknowledgement or sync or similar for UDP and HTTP. And once server started getting a lot of these requests, at some point it goes out of resources and then server just started going offline because it's getting so many requests, so many flood messages that it cannot handle. So these are the attacks they perform. During the Mirai attack, disrupted a few services, and that's the when all IoT community kind of had a wake up call that they have been doing a lot of research on IoT, but nobody thought that this kind of large scale attacks is possible. Uh, they did it, and they found the research. Hello.
शिवम
I can't.
કાતે પેલી સીઓમીઓ મેપ કરી હતી ને ઇન્ટરનલ નો સીઓપીઓ યુનિટ ટેસ્ટ 1
There is some disturbance.
હેલો શિવમ
This is a malware for you, Mr. Tushar.
All right. Looks like somebody just turned on their microphone. Anyways, so I was talking about like that was a wake up call for the community that hey, we need to come up with better solutions. Like we have to make sure that we protect our devices. There are some laws in California area specifically. They told all the IoT devices manufacturer to make sure that create devices without default username and password. Either devices should ask user to change their password or devices should come up with some sort of better default passwords, not like admin or admin password. So there are some protection mechanisms. You can do protection in 2 stages. First stage is against DDoS. So the last victim, the one who got a lot of requests, how we can protect him? Like if that entity is receiving a lot of requests, you can use something called NetFlow, packet analyzer, or IDS to kind of detect this kind of intrusion. And once you detect it, you kind of just flow all the traffic to some other servers, or you just stop getting new traffic, kind of throttling. So you can start throttling. And these are 3 mechanisms you can detect that there is a DDoS attack coming, and now you start throttling. Another is you actually protect getting more IoT devices. What if Mirai can never get 1 million devices? If Mirai can't get it, there is no way it will perform this DDoS attack. So there are some ways you can close the ports. Do not use default username password. Authorized device who is trying to connect. Few more. Use random default password. This is what the law California just passed to make sure that all the IoT devices manufacturer follows this. Or ask user to change the password before they use. Now, these are more in terms of users' perspective that users should either use random default or we'll ask them to change it. But let's see what we can do in terms of technology. So we can actually block logins after certain failed login attempts. So just remember, for me, right, they use 48 sets of password. Let's say you are one of those device. Still, on an average, the IoT, on an average, each bot should use 24 passwords to get through the actual password. So that's where, if you block the logins after certain failed logins, it should print after 3 failed logins, you just preempt getting new logins. You can time out the login request also. So let's say you failed 3 logins, 4th one, you cannot do it immediately. You need to wait for 30 minutes or so. So this way you can perform some really nice protections. A really good thing you can do here is something called client puzzle. This is not a new idea. People has been doing this client puzzle since 1990s. But let's talk about it, how we can reuse this client puzzle to actually prevent our modern time issue. Now, client puzzle is pretty simple. Let's say there is this bot, or we call it now, it's a remote device, tries to log into IoT device. Now, IoT device will create a puzzle. Now, consider puzzle as a problem. It's more like a computer problem. So that means a computer needs to solve something, which requires some time, which requires to allocate some resources. Remote device will solve it and sends back the solution. IoT device will verify the solution, and then it will ask like, hey, just give me your credentials. And once the credentials are provided, it will do the authentication. So this way, we can actually perform the client puzzles. We can actually prevent them, because now here, between the puzzle and puzzle solution, remote device needs to solve the puzzle. And we can make this puzzle harder every time it performs a failed login. This way, we can make sure that remote device is delayed and putting enough efforts to do that. Now, puzzle creation and puzzle verification should be pretty fast. And there are there are many puzzles available where creation is pretty fast, verification is pretty fast, but when you want to solve it, you need to put a lot of efforts. So that's what client puzzle can do and can prevent a big attack for IoT login. We can use adaptive complexity, the way I mentioned. Every unsuccessful login increases the complexity. Successful login resets it. Now, what happens is, at some point, puzzle will become incomputable. That means it is so hard to solve the puzzle that it will take months or years. And at that point, the remote device cannot log into IoT device because there is no way it can solve the puzzle, and now it's incomputable. Now here is a big issue. Now, the attacker can misuse this thing. There's something called Sybil attack, where you just send multiple false login requests. That's it. And this will just increase complexity for benign user. So now I'm really legit user. I cannot log into IoT device. Why? Because there are some attackers who just started sending false requests, and now when a benign user trying to log in cannot, because the complexity is too high. Now that's a problem. And then there is a solution for it, login puzzle. Now this login puzzle was one of my research, which I did during my PhD. We wrote a paper, we published in a conference for this. So this is the actual the research which me and my advisor we worked on at our distributed systems lab at University of Texas at Dallas. Now let's talk about login puzzle. Now login puzzles are similar to client puzzle, but instead of sending a really big puzzle, we just divide it into mini puzzles, small mini puzzles. The aim for login puzzle is two things. First, continuous resource allocation. That means the bot who is trying to connect should allocate continuous resources. So in the previous scenario, you just say that it sends the request, a fake request, and then it never tries to solve it. It just tries to increase the complexity without putting any resource. You need to put some resource to make sure that you are actually genuine enough to try. So that's what this login puzzle does. Instead of sending a big puzzle, it solves so many small puzzles. And because it's sending so many small puzzles, it's kind of ensures that it's continuously being, the resources being allocated, and it provides minimum penalty to benign user. We'll see how it can provide the minimum penalty to benign users. Now, there are two types of complexity, a linear increment. So in linear increment, we just increment the number of mini puzzle to one by one, or increase complexity of one mini puzzle. That's it. That's like linear increment. Exponential increment is like you're doubling the number of mini puzzles or increase the complexity of all mini puzzles. So this will become exponential because now we kind of increase it 2 to 4 and then 4 to 8 and then 8 to 16 because you are increasing complexity. Like here you are doubling, you are just increasing the complexity and making it double in a way. Now let's see the mechanism here. Remote device tries to log in, we create a puzzle, send a puzzle, puzzle solve, puzzle verify, uh, and if credentials. So this is like kind of a normal client puzzle, the way it works. Now this is more like login puzzle. You create a puzzle, send the first mini puzzle, you solve it, solution one, you verify, you send puzzle two, and you keep doing it. Now this way, you cannot just left it hanging that, hey, I send a request, you create a puzzle, and I'll send another request just to increase the complexity. No, it won't increase the complexity because you are not solving it. At some point, let's say the remote device stop like, oh, now it looks like it's too much. I don't want to solve the puzzles anymore because I'm a fake user. I'm not genuinely interested to solving the puzzle and sending requests. I just want to increase the complexity. The next login needs to solve puzzles which are not so. Let's say there are like n puzzles. This remote device solve 3 puzzles. The next one needs to solve n minus 3 puzzles. So this way the increment is linear. It's not exponential. In this case, it will exponentially continuously increasing, makes the life of benign user miserable because they need to solve a lot more puzzle because some remote device tries to log in with a lot of fake requests. And this is more like what happens when 2 parallel requests comes in. They both get puzzles. Let's say remote device 1 solves it first. And if the credentials are wrong for remote device 2, will just increase the complexity for remote device 1. Because it's still underway, we can still increase it. Should not be an issue. Benign penalty. Now, attacker sends multiple requests and didn't solve puzzle. As I already explained, puzzle increase complexity linearly. Benign penalty would be like, there would be still penalty because the complexity still increased linearly, but it will be minimal. It won't be exponential. Some performance analysis, client puzzle, yeah, both of them provides a login delay. Like even for client puzzle, if someone wants to solve it, they still need to solve it with some delay. Benign penalty is minimum here for client puzzle. Yeah, there is. There's no resource allocated assurance. As I mentioned, you send a request, you don't solve it, and then you send another request. No, it's not possible for login puzzle. It's still possible for client puzzle. And here are some stats that Mirai acquired 64,500 devices in 20 hours. What if all of those devices were using login puzzle? How much time it will take for login puzzle to, if all of these devices are using login puzzle instead of normal execution, if all those computations are happening on a Raspberry Pi, it will take 59 days to actually capture 64,500 devices, 42 days for MacBook Pro if all those puzzles are solved on MacBook Pro. If it's on AWS, very big server, like it has like 96 GB of RAM, 64 cores, it will still take 26 days. So yeah, it would be a lot of efforts, which they did it in less than a day. Would require 26 days now. This would be a good enough time to find such network pattern that, hey, some malicious things is going on. So this is the analysis for the login puzzle. And yeah, this is the last thing I want to discuss for IoT security. Thank you, everyone. Now it's like we have still 10 minutes. Anyone has any questions, any doubts? Anyone?
Hello.
Yes.
Any questions from participants?
Sorry.
No, this is
Yeah.
this is sir. I'm just talking to participants.
Oh yeah.
Any
Sure.
questions from participants? Okay, so on behalf of EC Department, I would like to thank Dr. Tulsisa for giving a wonderful and healthy sessions on security issues in IoT, right? So let me conclude our sessions. Still, if you have any questions, you may ask. We have 5 minutes for the question answers. Anyone? Okay, so Tulsisa, thank you so much for giving the wonderful sessions. And we will conclude our session right now. Thank you. Thank you very much.
All right.
Thank you, Trushit,
Thank,
and it was really informative session. We are
yeah.
really glad to have you.
Yeah. Thank you. Yeah. Like it's. I'm glad that you liked it, and yeah. Thank you so much for giving me such a nice opportunity. Uh, and yeah, I see someone saying that is it possible to share the presentation? Yeah, I can share it. Should not be an issue. I'll send it to Bhargav sir. But again, I hope it's informative and yeah, thank you so much for the opportunity.
Okay, so we will conclude this session, and dear participants, the next session that will be start from 1:30. Okay,
No,
thank
it
you.
is
Thank you very
starting
much.
from 1.
Okay, okay, sir. Okay,
I
okay,
think
sir. Let's start
schedule,
from
if you can look at the next session, is starting little earlier,
okay,
right?
okay. So we will gather at 1 p.m. Thank you.